2020. Already from this early morning, we have heard and seen presentations from almost 100 papers on various topics in both ICACSIS and IWBIS. From these presentations and the accompanying discussion, we hope that all participants gain a lot of fresh ideas, received novel insights, and uncovered new direction for future research and collaborations. And now we wish to end the first day with a bang. How? Well, at the end of the first day, we are very happy to host one of the world luminaries in the field of computer science. He is Professor Anil K. Jain, a University Distinguished Professor at Michigan State University. He is a fellow of IEEE, ACM, and SPIE. He is a world-renowned expert in pattern recognition, machine learning, computer vision, and biometrics recognition, and he currently holds the highest age index in the world in the area of computer science. In a minute, we'll hear him sharing his knowledge, experience, and insights on his work. This is a great opportunity for everyone, and I hope everyone is very excited to hear him in the next hour or so. His talk will be moderated by the chair of IEEE Indonesia section and a professor at Universitas Indonesia, our one and only Professor Wisnu Jatmiko. Professor Jatmiko, the floor is yours.
Okay, thank you, Dr. Adila. Yes, we are very happy because this is very special time. We have a special guest. Dr. Adila already introduced to us. Yeah. Prof. Anil Jain is maybe a researcher with the highest edge index in the field of computer science, with edge index of 190 and more than 200,000 citation. That is so, I think is so great achievement. Okay, please give applause for our plenary speech, Professor Anil Jain. Okay, without any further ado, now please welcome our plenary speaker, Professor Anil Jain from Michigan State University. Please, Prof. Jain.
Thank you very much, Dr. Vishnu and Dr. Adila, for your kind introduction. I'm very happy to be giving this talk, although I wish I was in Indonesia because I have very fond memories of Indonesia. I've been there 5 times. And last time I was there was 7 years ago when this conference was held in Bali. We are living in very difficult times. And so please take care of yourself and stay safe because COVID is not controlled yet and there is no vaccine. So it is very important for us to be careful. So what I want to talk to you about is what's going on in the field of pattern recognition, machine learning, and artificial intelligence. Of course, now the terminology keeps on changing. In the 1950s, 60s, and 70s, it was the pattern recognition and artificial intelligence. And somehow artificial intelligence researchers thought that they are doing better work than pattern recognition. And then came the field of data mining, data science, and then machine learning. And so terminology keeps on changing, but the problems still remain the same. And now everybody claims that they have a artificial intelligence system, even though there is very little intelligence in the system which they are delivering. So let me first start out with this small video from Amazon about the drones. As you know, drones are not new, but this is a drone which can deliver packages to your home. And I'm sure now, especially with the COVID situation, you have you have been ordering things online through whatever websites you have for delivery. So now FAA is the Federal Aviation Administration, and so they have given approval to Amazon to deliver packages, and pretty soon you can get your food delivered, your medicine delivered, and this has other social benefit. I mean, Indonesia is a vast country with many, many different islands, and sometimes transportation is difficult. And so if there is a disaster, natural disaster, it's easy for the drones to deliver whatever medication, food is necessary to remote places. So this has very important implications all over globally. Another interesting achievement is from Japan's. They have their flying car gets off ground with a person aboard, and the only space it needs to land is just two parking spaces for car. Okay, and this is amazing because as we all know, Jakarta traffic is bad. Okay, so suppose you have this flying car which is sitting in your home, you can simply go and not take any congested highway in order to reach your destination. Of course, the autonomous vehicles, self-guided vehicles, have not been as successful as originally thought, and the reason is because the intelligent system which they have on the autonomous car sometimes cannot tell the difference between a pedestrian or another car. And this has been a serious problem in some accidents. And all it takes are few accidents for people to lose the confidence. So people may say that this is an artificial intelligence system. That's fine. But what is artificial intelligence? In order to design such vehicles, you have to have aerodynamics, you have to have control mechanism, you have to have computer vision system, and now everybody is using deep networks. So that's why the title of my talk is From Statistics to Deep Networks. People are from model driven to data driven, right? I mean, earlier we used to assume that the pattern classes have Gaussian distribution, and then we design a classifier. And then now we are focusing more on data driven. We have a deep network, all we do is feed in the data, and out comes the answer or the decision. So that's where the field is heading. But I think it's very difficult for people to comprehend that how do we design such a vehicle? We call it artificial intelligence, but artificial intelligence is not just one concept. It's a combination of many different concepts. So what I'm going to talk about is a little bit about the history, beginning of artificial intelligence, beginning of pattern recognition, and how they have merged now. Then there is this alphabet soup: artificial intelligence, AI, PR is pattern recognition, NN is neural networks, DM is data mining, DS is data science, ML is machine learning, and DNN is deep neural networks. They all have similar goal, but we keep introducing this terminology, and it's very important for us researchers to understand, what problems are they solving and how they are solving it. So that's where I want to talk about model-driven to data-driven approaches. And then as a case study, I will talk about face recognition, because face recognition is one of the most emerging technology right now, which every country is adopting in various forms or the other. Then there are issues of privacy concerns. Whenever you have an intelligent vehicle like a drone, there are a lot of privacy concerns. What are the privacy concerns? Somebody may be flying drone over your house and getting all kinds of information. Who is living there? What are they doing? And things like that. And that's rather dangerous. So how do we control that? How do we avoid? We have a lot of surveillance cameras, growing number of surveillance cameras, and we are walking by. What are they going to do with those images? And then something about the next decade of artificial intelligence. So the use of the word artificial intelligence was introduced only about 70 years ago. I mean, there was a workshop held by some famous AI researchers at that time: McCarthy, Minsky, Rochester, and Claude Shannon, the information theory person. And they said that the goal of AI is to make a machine behave in ways that would be called intelligent if a human were so behaving. Okay, so flying a plane or driving a drone, controlling a drone is one example of an intelligent machine. And then they also introduced something called the Turing test. Okay, and Alan Turing, whose movie was also introduced 5 or 6 years ago, and the Turing test said introduced what is called the imitation game. Okay, some of you may not know about the Turing test, but now because people have forgotten about it, because Turing test is too difficult for a machine to pass. But basically, it said that it tests if a computer can successfully pretend to be a human in a dialogue via screen and keyboard. So suppose on one side of the screen is a human, on the other side is a computer. Okay, and if the human cannot tell the difference, who is sitting on the other side, a machine or a human, then the machine passes what is called the Turing test. And the only way the human can communicate on the other side of the screen is via a keyboard. He cannot talk, he simply can give some commands or ask a question through the keyboard. So this is the beginning of the AI. And then what about the pattern recognition? That's also relatively new in the sense that it was only also introduced around 1955. And by pattern recognition, we mean the extraction of significant features from a background of irrelevant detail. It is the kind of thing that brains seem to do very well that computing machines do not do very well yet. So the key thing here is significant features, extraction of significant features. And in order to extract the features, that's not an easy task because it is a domain-dependent task. For different domains, you have different set of features. If you want to do image analysis, you have a different set of features. If you want to do speech recognition, you have different set of features. And so that has always been a stumbling block in designing a recognition system. So that's where deep network comes in, because deep networks avoid explicit specification of features for any recognition problem. You simply input the raw data, raw image, or raw signal, and the features and the classification are learned jointly from the large amount of data which it needs. So when I first started graduate work in 1969, the AI researchers were claiming that their goal is designing general purpose intelligence. When I say general purpose intelligence, they wanted to have a machine or an intelligent agent that could solve multiple tasks at the same time. That is, it can diagnose a disease of a patient with the patient is suffering. It can play chess, it can play dominoes. But unfortunately, as we all know, that has not been successful. And that led to what has been referred to as the winter of AI. That is, there was no activity. The claims made by AI were so outrageous, and they were not successful in delivering that people forgot the interest in AI. On the other hand, pattern recognition had a much simpler goal of domain-specific intelligence. That is, let's just solve a task in a particular problem, whether it is character recognition, fingerprint recognition, and so on. They never claimed that we will have a general purpose intelligence which will solve a variety of problems. So general purpose intelligence has been elusive, and most AI researchers now focus on specific tasks. And so in that sense, AI and pattern recognition have converged with the same goals. And that's true with machine learning, that's true with data science or data mining. So when we want to design an intelligent system, there is not just one thing which we can learn and say, oh, now I'm ready to design intelligent system. So the examples I showed you earlier of a flying drone and a flying car, in order to design such a system, we need a team of multiple experts. We need some people who can do image and signal processing, machine learning, pattern recognition, deep network, security and privacy, domain knowledge, And then so the artificial intelligence encompasses many things. And then I couldn't show some of the other things, for example, embedded systems and faster processors and so on, because when you want to design an intelligent system, everything should be on board, especially for flying car and drones. It's not that there is a guide, there's a signal coming from the ground telling them what to do. So everything has to be processed online for real-time operation. So this is very important to understand that, depending on the domain application, or if we want to build a real system operating in real environment, the system must be able to sense the environment using different kinds of sensors, learning different domains, utilize the domain knowledge and other things. So if you're flying a drone, it has to be aware of what terrain it is flying over and things like that. So I want to also talk about some of the most influential technologies which Washington Post, the newspaper, well-known newspaper published in Washington, D.C., about over the last 10 years, which are all consumer-facing technologies. So first we had this Facebook's news feed. So basically it learns the user's habits or user's preferences and provides the news items in a capsule form to you. Then there came the Netflix streaming, and there is sort of a recommendation system built in it, which based on the movies which you have watched before, it recommends it recommends other movies which you may like to watch. Then we had the Facebook's Instagram, which in 2010 it was introduced. Then Uber introduced a semi-autonomous vehicle. I say semi-autonomous because the driver always has to have his hands near the steering wheel to take over the control. It is not an autonomous. And Uber has been trying to have an autonomous vehicle, but with a few accidents, it had to sort of downplay its claims and wait for the technology to be perfected. And maybe it will never be perfected. Then we have the Tesla's Model S, which has been quite successful, but again, it's a semi-autonomous operation. Then we have Apple's iPad, which is a major achievement in 2012. Some of you may be aware, this is the Amazon's Ring doorbell, which has a camera in it. And so when somebody comes near your door, the camera captures the videos of who is coming there and then alerts the homeowner in case there is a threat. In 2013, Apple introduced a fingerprint recognition system in their mobile phone. In 2014, Amazon introduced the Alexa, the conversational system with whom you can answer questions and so on. In 2015, the Apple Watch. And 2017, the Face ID in the mobile phone. So these are some of the technologies which we will call intelligent in some ways, which are all in the consumer market, and we utilize them. So designing such a compact, intelligent machine, even though you have very fancy machine learning algorithm, is not easy. Packaging everything, the usability of these devices, that's another important thing. So for example, Apple Touch ID, some of you I'm sure have used it because Samsung and other companies, Chinese companies into phone also have that. The key thing here is the usability, putting the fingerprint sensor under the home button, and everybody uses the home button. That is quite an achievement. Earlier versions of the mobile phone by Motorola, which had a fingerprint ID system, the fingerprint sensor was at the back of the mobile, and that was not very easy or convenient to use. So this transformed everybody. And now, the cost of the sensor and the fingerprint matching algorithm is not very much, because hundreds of thousands of these mobile phones are sold. So you can get what Apple pays for the fingerprint reader and the matcher is about $1. The rest of the cost is of the mobile phone. Same thing with Face ID. Face ID is a little bit more expensive, maybe $5 or so. So this I have already shown you. And then with the artificial intelligence, there's also a lot of hype. Okay. So for example, the washing machine, I forget which brand it is. Let's see. Washing machine with artificial intelligence. You know, it is simply checking what is the load size, and it adjusts the settings based on the load and what kind of clothes it is. So you can call it intelligent, but it is not the same way as designing a, a flying drone and flying car. And then the Ford Motor Company CEO admitted that we overestimated the arrival of autonomous vehicles. So, so the hype surrounding AI has peaked and troughs. That is, it went through highs and lows over the years as the abilities of the technology get overestimated and then re-evaluated. So let me now go to the basics, which I teach in a pattern recognition class. And in some sense, it is also taught in machine learning, AI, data science. The goal is to recognize a pattern, and the pattern could be anything. It could be an abstract pattern, it could be face, it could be some natural pattern like peacock feathers. It could be some wild animal with an interesting skin texture, and fingerprint. And notice in the lower left image is the new disaster, the COVID virus. And we didn't know about this image 1 year ago, but now everybody has seen this virus structure all over the media. And then there is a notion of pattern class. So if you want to do digit recognition, character recognition, design assist machine, which will recognize the trees, then we need to define a class. When we say tree, by tree, it is a concept. That means it has some members. So what is the characteristics of these members? It is a collection of similar, not necessarily identical patterns. Now notice that there are so many different types of trees. It's very difficult to have a model for that tree. How do we define a tree? I mean, we can say, well, it has a trunk, it has some branches, but a telephone pole also has similar structure. The leaves fall in certain season, so the tree may be bare, the tree may be in bloom. So it is very difficult to come up with a model to define a tree. So how does a child learn what is a tree? The child learns when the parents show many examples of the tree, and the child automatically learns. So that's how a pattern class is defined, either by a model or a whole bunch of examples. And that's the difference between the model-based and the data-driven approaches to recognition system. And that's the difference between statistics and deep networks. A model, earlier we always modeled the pattern class in terms of statistics, but now deep networks have come in and they are driven by large amounts of data. Then the question is, how do we define representation or features and similarity, which are fundamental to intelligent systems? Okay, so there are two concepts here: representation, which is the feature, and similarity, which is the classification. And again, either we can take a model-based approach to it, or the data-driven approaches to it. Sometimes when we take a model-driven approach, we define the representation of features as handcrafted. That is, the designer of the pattern recognition system is specifying what features to use. But now with the deep network, representation and similarity are learned jointly. So then we define this notion of intra-class variability. Here we have the same person. Some of you may know who he is, Mahatma Gandhi, the India's non-violent activist. And here we have multiple images of Gandhi. Those who have seen Gandhi once will recognize all of them as Gandhi, right? So if you design a computer vision system which just uses the pixels, that would not work because the pixel values are completely different, and that's why we need a representation, a high-level representation of features in order to do the classification, right? So intra-class variability means patterns within a class, how different they are. The lower the intra-class variability, better the recognition, right? So that's why printed characters are easier to recognize if you're working in character recognition than handwritten signatures or cursive script. Then this is what is called the interclass similarity. So if you're doing face recognition, one of the challenging problems in face recognition is distinguishing identical twins because they have all they have very similar appearance. So this family in China had a quadruplets, 4 identical twins. And neither the parents could recognize sometimes, nor the teachers in the school. So they gave them a hairdo, a tattoo form of hairdo with the digits 1, 2, 3, 4 to distinguish who they are. And this is a serious problem. And how did Face ID in Apple avoid that? By using a 3-dimensional face recognition system where they use a depth face image to tell the difference between the facial structures. Okay. So in all these problems, the challenge is to learn a compact and discriminative representation for pattern classes. Whether you call this machine learning, whether you call it data mining, pattern recognition, or AI, or computer vision, they all mean essentially the same thing. They all have the same task. So I just want to show how multiple representations can boost the recognition performance. One representation often alone is not sufficient, depending on the complexity of the pattern. So here we have a fingerprint pattern, and the most common features for the fingerprints at level 1 are these singular points, cores and deltas. And then we have the second level feature, which is which are the minutia points along the ridge endings and ridge bifurcations. These are all handcrafted features, which the forensic scientists all over the world use it to identify a person based on fingerprints. And there are now fast commercial systems called AFIS, Automated Fingerprint Identification System, which also rely on these features. And then you can also put some graphical structure on it. And now, with the introduction of deep networks, you can use a deep network to get a fixed length representation of the fingerprint. In this particular case, I'm showing a 192-dimensional fingerprint representation. And a fixed length representation is much faster than the variable length representation like minutia points. And so a combination of both minutia points and fixed length representation gives you state-of-the-art recognition performance. So basically, it's like what was often called a society of experts. That is, when you go to a medical doctor and they diagnose a certain disease, often you would like to go and get a second opinion. And that's what the representation is doing. It is taking multiple looks at the same pattern and coming up with a different description. And then, of course, we have two different recognition problems. One is assign patterns to known classes. Known classes, this is referred to as classification or supervised learning. And the second one is called arbitrarily defined classes or group, and that's referred to as clustering or unsupervised learning. Okay, and so we can use a variety of methods, classification methods for doing this. So here is an example of grouping where I did not provide labeled patterns, and it's automatically labeling cats and dogs into two different classes. So clustering or unsupervised learning is more difficult than classification or supervised learning. So let me now start with some technical definitions. The first model-driven approach, linear discriminant, was proposed by R.A. Fisher, 1936. So what we take it for granted, we may not know, was introduced almost 90 years ago. Okay. So basically, you have a feature vector, handcrafted feature vector. You have labeled data, training patterns from the two classes. And basically the model he assumed is that there are two Gaussian distribution, one for class one, one for class two. Of course, it can be generalized to multiple classes. They have the same covariance matrix sigma, but different mean vectors. Okay. And the learning involves estimating the model parameters, mu1, mu2, and sigma. And in this particular case, we have a relatively small number of parameters. If there are n patterns, then there is a n-dimensional vector mu1, n-dimensional vector mu2, and n by n covariance matrix. And since the covariance matrix is symmetric, the number of parameters is essentially n times n over 2. And then came the first data-driven approach, the perceptron, which was also introduced in 1950s, 1958. So notice that, the definition of AI, the definition of pattern recognition, the perceptron, they all came around the same times in 1950s, with the model-based method came a little bit earlier. So that was a very active period which put the foundation for what we do today. So this was Perceptron by Rosenblatt, was called the first biologically motivated network that learns to classify. So basically it has one neuron which takes all the input features, properly weighs them based on the weights Wi, and then there's a function which acts as a thresholder to determine whether the input pattern belongs to class 1 and class 2. So we again have these features. We have labeled data from the two classes. And now what is the network learning? The network is simply learning the network weights, which in this case is W0, W1, Wn. W0 is the bias, and W1 to Wn are the weights assigned to the n features. Okay, so learning is essentially the same thing in both model-based and data-driven approaches. It is the parameters, but the parameters have different interpretation. In the Fisher's linear discriminant, the parameters were the parameters of the density function. And here we have parameters of the network connections. So many of you may remember this was what Fisher originally introduced the iris data, 3 classes of iris, and he defined handcrafted 4 features. And the reason I'm showing you is this is the historical development and how model-based and data-driven approaches classify such a data. So in a linear discriminant, Fisher linear discriminant, it's a deterministic system. You estimate mu1, you estimate mu2, and you estimate sigma, and you get a boundary. In the perceptron, it is an iterative algorithm. It is learning the parameters of the weights of the network. So you start out with some initialization, and then you try to classify the training data as best as you can, and then you get a trained network, and then you can do the classification. So in this case, the first time I show the hyperplane, that was an initial randomly chosen weights. And then after 2 iterations, it separates the data perfectly. So this is referred to as perceptron learning algorithms, which means that it will work if the data is linearly separable. Of course, we don't know high dimensional data, whether it is linearly separable or not. And that is why neural network was introduced in 1980s. That's when they had multi-layer perceptrons. So now we have going to linear to quadratic classifiers and SVM. The difference between the quadratic classifiers and SVM is that the quadratic classifier assumes different covariance matrices, as opposed to Fisher's linear classifier, which assumed a common covariance matrix. And the SVM support vector machine is a nonlinear kernel, which transforms the data to linearly separable case. But now, with the introduction of deep networks, nobody is using SVM. Everybody uses the deep network. So what we learned over the past 40 or 50 years is essentially now pretty much gone away. Although I think the students and professors should always know the history behind it. And there may be some problems where the deep networks would not work. So then, as I mentioned, from perceptron, we moved to uh, multi-layer neural networks. So perceptron has only one layer, okay? And in this case, if we have 6 features, we have 7 parameters to learn, okay? Now here I'm showing 2-layer network. Perceptron was 1-layer network, and now I'm showing 2-layer network. We don't count the input layer and the output layer to define the number of layers. The hidden layers are what is critical. So we call this the 2 hidden layer neural network. And if you do a counting exercise, how many parameters there are in this network? It is 47 different parameters. So the 47 is a function of how many features you are using. If you are using hundreds of features, the number of parameters will be in the order of thousands. Okay, and so one of the major developments was a backpropagation algorithm. How do we learn these parameters when we have multiple layers? Okay, the advantage of the neural network, multi-layer neural networks, is that it can solve nonlinear classification problems. And so now when we talk about deep networks, it's nothing but a multiple layer neural network. The reason why we use the word deep is because it has more than 2 hidden layers, which people had thought earlier, but they didn't know how to train it. Now notice that since the number of parameters has increased from perceptron to 2 hidden layer neural network, there are more things to learn, so you need more data. I mean, you cannot avoid that. We know that when we have larger number of parameters to learn, we need larger amounts of data. And that's what the requirement of a data-driven approach is. You must have a large amount of data, whereas model-driven approach can manage with smaller amount of data. So here is an example. We have an input data on the upper left. One class is shown in terms of red circle, the other class is shown in terms of blue dots. It is non-linearly separable in the sense that there is no linear hyperplane which can separate the red circles from blue dots. We have a quadratic classifier based on Gaussian density model with a different covariance matrix. We have a 2 hidden layer network, and then we have SVM. Okay, so this shows that all these models or data-driven approaches are doing the same thing, but they're going about doing it in a different ways. So now we talk about the deep networks. It is an end-to-end approach to jointly learn features and prediction. So what the model-based methods do, we have a data, we have some handcrafted features, x1, a vector x, and then we have a learning algorithm, which could be a linear, quadratic, SVM, or whatever you want, and out comes the prediction. Okay, and there's of course a training involved, which is to learn the parameters of the algorithm. And then we have the deep networks, which is data and a network And the features and the classification or prediction are learned within this network, and out comes the prediction. So basically, we have collapsed the handcrafted features and learning algorithm into one box. So now I want to just briefly talk about face recognition. I'm also watching my time, so I only have 5 minutes left. So we have face recognition. Now, why is it such an important problem to solve? Well, first of all, we have every country in the world now has large number of CCTV cameras, which are all networked. And why is there increase? Because of for a variety of reasons, for security threats uh, you know, there are 600 million CCTV cameras going to be in China alone by next year. So there's an amazing increase in the number of surveillance cameras all over. We also are using face recognition when we enter into the United States. Um, there are these self kiosks where you can simply uh, uh, scan your passport, which has a photo, and you take a selfie using the camera on the kiosk, and then it prints out a slip, and then you just talk to the immigration inspector for half a minute, and then you're out. Okay, this is a good way to avoid long queues at the immigration checkpoints. And then when we now recently, over the last 1 year in the United States, they also have a face recognition system when you board an international flight. So the use of face recognition has been growing, and the reason for that is that the recognition accuracy of face recognition has improved a lot. I want to show you this. This is supposed to be I thought a video, but it's not working. Basically, Amazon now has a store called Amazon Go. It is a small convenience store. It's not like a big supermarket where you can, after the office, you can pick up some things for cooking dinner or for your breakfast. There's no cashier. You simply use a mobile phone to get inside, and then there are all variety of sensors on the ceiling, on the shelves, and as soon as you pick up some item, the system knows what you picked, and it also recognizes your face, that the person who is using mobile phone to enter the store is also is really the owner of that mobile phone, and then it automatically deducts how much money from your account you purchased. So this is a kind of a system where face recognition and other sensing technology and recognition is becoming very, very advanced and very useful. So there are two problems in face recognition which are extremely important. Authentication. So in this particular case, this is my former postdoc, Shao Kai. This is the scan. On the left is the scanned copy of his driver license. On the right is his selfie. And now you can do authentication by matching a degraded, low quality face image to a high quality selfie. And this can be done for home shopping. So for example, the bank wants to know, or the credit card company wants to know who is making the purchase. Well, you go through this face recognition operation, and the credit card issuer or the bank knows, yeah, the purchase is being made by a valid customer. And then there's a problem of search, which is more challenging. And this is what is done in a surveillance system. If the police wants to know if a terrorist or some wanted person is crossing the street, they will constantly capture the face images from the surveillance camera, send it to the central face recognition system, which will find a person of interest. So you have a probe image and you have a gallery, which is the database, and you search it and you find a person with the most similar face there. So this kind of a technology is now being routinely used in a variety of applications at immigration checkpoint. Before you even come and talk to the immigration officer, it can determine who you are. And this is where I want to show you how deep network has so changed the face recognition landscape. Every commercial company which sells face recognition system and every academic group is using face recognition system. And it all started from a 2014 paper in CBPR from researchers at Facebook called Deep Face, closing the gap to human level performance in face recognition. So just in last 5 or 6 years, the whole landscape of face recognition has changed. But this has been possible because we have huge amounts of face training images. You cannot train such a network with millions of parameters with only a few hundred images. So ImageNet is for object recognition, and we have all kinds of face images, tens of millions, which have been scraped from the social media websites. Then the reason why deep networks are so popular is because of the powerful GPUs, which you can put on your desktop or even laptop. So this is the most important chart I want to show you, how the object recognition accuracy after deep network was introduced has changed. So the using the traditional methods of object recognition, sparse coding and SIFT, okay, we have a continuous sharp drop in the first use of AlexNet from 25% error rate to 16% error rate. And since then, with using a variety of object deep network models, we are now down to this challenge, ImageNet challenge stopped in 2017, and now it has object recognition accuracy on this database has dropped to 2.25%. And what I showed us in the dotted purple line is what will be the error rate of the human in the same classification task. And you notice that now machines can do better than humans for certain tasks. But we have long ways to go in face recognition. If faces are better aligned, like on the left, we have a very highly accurate face recognition system. You know, there are 3 subjects, and each row shows 3 images of each subject. But when you have a very challenging face images from a surveillance cameras and other sources, then the accuracy of the face recognition system is very small. So I think I will skip some slides. Professor Vishnu would make these slides available to all the participants. I have already sent him the PDF version. So let me just go to the conclusion because I don't want to. This is another challenging problem. If I showed you these 6 images and I tell you some are fake and some are real, you know, it's not easy to tell. With the high quality color printers and tablets, it's very easy to fool a face recognition system. And so here, based on the work we have done, this is the correct answer to that. The images in the green boxes are real faces, and the images in the red boxes are fake faces. So to summarize, many of our daily tasks involve recognizing patterns, vehicles, pedestrians, voices, trees, buildings, and there have been 2 approaches, model-based and data-driven. Training a recognition algorithm needs large labeled data. Deep networks are now popular. They're data-driven, so no need for designing complex models or finding which is a good model for the given problem. But deep networks require access to large data, and the state-of-the-art, it provides state-of-the-art performance for object recognition, face recognition, and speech recognition. But deep networks are brittle, and they also cannot explain their actions. That is, since deep networks takes as input the raw signals, slight perturbance in the signal or the image causes them to behave very erratically. And then compared to the previous AI winters from 1974 to 1980, 1987 to 1993, when there was very little activity in artificial intelligence. People are concerned that with too much hype about artificial intelligence, we may have another AI winter. So I think with that, I will stop. I want to give you enough time to ask questions. So, Professor Vishnu, thank you very much for inviting me, and I'm happy to answer some questions now.
Okay, thank you, Prof. Jane. It's very impressive and interesting presentation, and your explanation is very remarkable and interesting. And we believe the attender will explore more about the pattern recognition because we uh, know about your track record, as you mentioned before, uh, about more than 40 years you are deal with the AI and so on. Okay, actually there is some question more than five, but actually I just cluster about the point. Uh, the point is I choose the interesting one is how about the general AI, Prof. Jane, as you mentioned before. Usually we have some, I don't know, the next winter AI maybe, for example, and we
Right.
overestimate about the capability of the AI, but in the real implementation is everyone may be not happy or not satisfied. How about the general intelligence, artificial general intelligence? It will be happen, and can the intelligent machine replace the human? This is a majority of the question from the Q&A. Okay,
Right. I
please,
think
Prof.
I
Jane.
think it will be. I think it may be very dangerous to deploy a premature system which will replace humans. We always have to have a human in the loop for many critical decisions, right? For example, if somebody is arresting a person based on face surveillance system, okay, it is well known that face surveillance systems make mistakes, machines make mistakes,
Mm.
just like humans make mistakes. Humans have their own bias. They may not like a person of certain color, which happens in the United States. So the key thing is to have the top 10 candidates by face recognition system rather than saying, oh, I'm sure this is the person on the surveillance camera. You give the top 10 candidates to the police and then let the police make the final decision because arresting somebody for a crime is a serious thing. It's the same thing with the medical diagnosis system. Some
Mm.
of the early work in AI was to take a patient's all the measurements on the patient's data, for example, X-ray, blood test, blood pressure, and so on, and then make a decision on what is the disease with which a patient is suffering. Now, you don't want to put a life-threatening thing in machine's hand. That is, if the machine says, "Oh, this patient has a cancer," or machine says this patient has no cancer, but if the machine is wrong, that's a life-threatening decision. So, for a routine task like sorting mail in a post office in the United States, all the mail which comes to the central post office gets sorted by character recognition system, which puts the mail in different bins based on the destination, right? So that kind of a thing is okay. Autonomous vehicle, there's always going to be a driver in the loop where the machine will alert. I'm not sure where I am, or I'm not sure who this person is. Just imagine somebody crossing the pedestrian lines on the road, and the headlight is red, but it is the traffic light is red. The car is supposed to stop, but it is really raining
Mm.
and it's a cloudy day, and the machine vision system on the autonomous vehicle is not working, or the radar is not working, you know, and there is an accident. There is a huge implications of that, at least in the United States, where the lawyers are always eager to file a lawsuit. So I think for critical decision making, you can think of a airplane being flown by a machine, which happens these days. All the jet aircraft which we take in for international flights, they're pretty much self-guided, except the pilot is still sitting in case of emergency to do the take over the control, especially during landing and takeoff. Okay. I also noticed there was a question about the privacy. I think that's a very critical question, because every country is now realizing we are putting too much faith in technology, and technology is collecting our data. So there was a concern about this Alexa from Amazon or Google Home, uh, because every time we speak, they are using our speech pattern for improving their algorithm as training data. Okay. They didn't ask you that you didn't know when you bought that system that it is going to do that, right? Same thing with the doorbell, Amazon's Ring doorbell, which has a video camera in it. Okay. That's every time it captures somebody's face, it's using that to train a system. Facebook, they've been they've been accused of selling your data to third party. So these are all privacy issues. So how do we control it? The only way to control is for the government to have some privacy laws. That's the only way. And the privacy laws must have enough teeth to punish the companies. Without that, the companies are always in the business of collecting your data. I mean, why we don't pay any service to Google for Google search. We don't pay any service to Facebook for using Facebook. So how are they making money? From advertisements. And how do they monetize? So they monetize your data, personal data, to direct appropriate advertisements to individuals, right? They don't show us all the same ads, right? If I searched for a hotel in Surabaya, okay, every time I will log in, they will show us new hotels deals in Surabaya, right? So there's a whole new field called computational advertisement, okay? And pretty soon, we will have billboards. If you, some of you may have seen the movie Minority Report, right? Anybody seen that? Where, the cameras in the supermarket are taking your picture. And if they say Vishnu coming in, they say, Vishnu bought this jacket from me from the store last year. And they will show new ad of a new jacket, which is in the store now, right? Just imagine that you are walking on the street in Jakarta and there is a billboard, advertisement board, which has a camera in it. Okay. And if Mia goes by the board, a woman goes by the board, young woman, they will show an ad of cosmetics for the woman. Okay. If Vishnu goes by, they will show some other ad, right? So they are not particularly doing, in that case, a face recognition, but they're doing gender, age, and some demographic estimation, right? That's privacy, right? So the question is, of course, when you are in public place, you are open to this kind of surveillance. The question is, how will you use it? Will you use it in some harmful way? Right? In order to do that, you need the privacy laws, and many countries don't have the privacy laws except the European Union's GDPR, General Data Privacy Regulation.
Okay, very interesting, Prof. Jane, because still have many open problem and still a big question. But I represent from my student. Usually they ask to me when we deal with the, as you mentioned before, forget it about SVM, forget it about so Now it's being replaced by a deep network, and in the deep network, we depend on the data, depend on like a black box. So sometimes we cannot explain with the mathematic background and so on.
Right.
What is your opinion? So I
Yeah,
can
that's an open problem. That
Mhm.
is an open problem. Explainability of AI,
Explainability of AI. Okay.
right? That's a major
Mm,
problem. How
mm,
do we interpret why the deep network made this decision?
mm,
Another problem with the deep networks is that they have some bias at least from the face recognition
mm,
perspective. They have some bias. They may recognize people from Java with different accuracy than people from a remote island, right?
mm,
And so because of the skin color, because of the gender, because of the age, they may have different recognition accuracy, right? And so the bias is an important issue. So for example, Google 3 years ago was accused that it classified a black man as a gorilla because it
mm,
hadn't seen enough examples of black men,
mm,
right? So bias. And the third thing is adversarial attacks.
mm,
That is, if I'm doing face recognition or object recognition just based on the pixel images, it is indeed possible that you can change some pixel values to suddenly completely change the object classification. You give an image of banana and change some pixel values, it becomes apple, right?
mm.
And you have heard of deep fakes,
Yes, defects as you mentioned
right?
before.
Right?
Mm,
This is all because of the deep networks,
mm,
right? So, yes, while deep networks have been popular and successful, but we still need to remember the problem domain is important.
mm,
You cannot blindly apply a deep network to your problem. You still have to understand what is the data, what is the noise in the data, whether the data is representative of the population. Okay. And how do we guide the deep network with the domain knowledge? That is also important. That's why one of the things which I didn't get a chance to talk about is a combination of top down and bottom up. Top
mm,
down means some domain information. Bottom up is strictly data driven. And
mm,
some combination of the two is always essential. You cannot work on speech recognition without knowing about how the speech is generated and what is the characteristic of the speech. You cannot just feed in some bunch of speech samples to the network. You have to do some pre-processing. You may have to do some alignment, some correction for the speed with which you are talking. This pre-processing is still very critical. Okay, in face recognition, often there is a face detector,
mm.
a face alignment. You cannot input arbitrary face images. So we still need to know about the domain knowledge.
Mm.
Okay, any
Okay.
other questions from the audience?
Uh, okay. I think
I can
because
stay and I can stay a little longer if needed.
but I don't know because in Indonesia it's almost 10 10 p.m.
Oh, I see, I see, I see.
But
Yeah.
I don't know. Is there any question? Okay, I will choose directly one or two question from
Okay.
the Q&A.
Okay.
Uh, just respect from the actually this is from Prof. Lens Fung. This is also the director Alex Region 10, Prof. Anil Jain.
Mm.
He joined with us. He said, oh, Prof. Lens Fung, will you directly discuss with Prof. Jain, Prof. Anil Jain? Can
Maybe
you?
you can ask. You can ask.
Oh,
That's simpler.
we already upgrade the become panelist. Okay. Please, Prof. Lensbung.
Okay, good evening and good.
What happened?
Can you hear me now?
Yes, yes,
Yes,
yes.
Okay.
yes.
Yeah, thank you so much for your presentation. It's really excellent and comprehensive, running down of all the comment. And I also see that we have already discussed about the general AI, which you have already covered, and also in terms of the trust and also the data privacy, all those things. But really, in general, how do you view that? Well, you have public figures, like Bill Gates, like Elon Musk. They publicly saying that they have concern about the general AI. So on the other hand, there are people like Andrew Ng saying that it's not really nothing to be concerned. It's still quite far away. And I perfectly agree with you. Because the AI or the deep learning we're using is a black box, so therefore people are not able to trust it. But you also mentioned about the use of the explainable AI. But I look at explainable AI is one thing is explaining how the decision is being made. Another aspect is can be explaining how the development of the model in the first place. Because a lot of time, when we look at papers, people just simply put in a black box and get it, but they didn't really give enough details on how the actual things are being developed, and also make the availability of the data so that you can repeat it. Because in other discipline of science, we expect it to be repeatable, but
Right.
really in AI study, we don't do that. So what is a comment on this?
Yeah, so basically there's a difference between engineering and science, right?
Mm.
In science, people will not accept your results. If you say, "Oh, I have a new vaccine for COVID," nobody will believe it unless you actually is evaluated by some independent third party,
Exactly.
right? But in engineering, the recipe is hidden inside their product. It may essentially be, the reason why Facebook, Google has hundreds of face recognition researchers or AI researchers is basically to fine tune the model. There are many kinds of deep network models. One is they're all different. Their concept is the same. It's the engineering which sets them apart and the training data which sets them apart. The data is now the new oil.
Yeah.
Okay, data is the new oil. So more data you have, more powerful system you can build. And you shouldn't be doing deep network if you don't have enough data, because you won't be very successful with that, at least from a commercial level, right? So that's why they will not reveal, because their secret recipe is in the data. Even if they publish their model, what they are using, they won't specify all the parameters and they'll never share the data with you, right?
Yeah, agree.
Whereas in science, it is very different. I remember very clearly, we published a paper in the Proceedings of the National Academy of Science on fingerprints uh, 5 years ago. And then it was a big stink because they were forcing us to reveal the data because one research group wanted our data. And we finally had to say that, look, the data came from a police agency, and police does not want to reveal the data in public domain. But the editor of the journal threatened us, saying, "Oh, we will withdraw your paper." So I said, "Okay, we will put the data in a vault,
Mm.
and anybody who wants to use it, they can connect the vault in one way. That is, they submit the code to the vault. We will do the evaluation, and then send back the results." Okay, and then finally that agreement was reached. But for many of the recognition systems like face recognition, speech recognition, there is an organization in the United States called National Institute of Standards and Technology, NIST. And NIST does a public domain third party evaluation of all face recognition systems, all speech recognition systems, and so on. So they have the ability to search a face recognition system on tens of millions of operational data. And then they publish the results. And they rank order the algorithms based on their performance. So if that kind of a thing can be done through a competition or whatever, then people have more trust in what's going on. So at
Exactly.
least if anybody wants to buy a face recognition system, whether the Indonesian government or some other agency, corporate agency, they all look at the NIST evaluations for face recognition, speech recognition, and so on. And now some conferences have started doing the competition on explainability and other things. But making the data available in the public domain is becoming more and more challenging because of the privacy issues.
That's right. I agree 100%. Then how about the IEEE, well, ethical aligned design? So we have been moving towards the standardization, well, through the IEEE Standards Association. And also, well, there might be even saying that in time to come, well, those intelligent systems need to be certified. So what is your move on your thought on that one?
If the public wants these tools, they will have it, right? So it's the, IEEE may have standardization policy, but it doesn't have much teeth in it. I think what we really need is safety protocols and privacy protocols from the government, rather than from professional organization like IEEE. These are guidelines. And they're useful guidelines. I've been an IEEE member for almost 50 years, but I think it is beyond IEEE to force the companies to do some things. IEEE standards have been very useful for a variety of situations, but when you are talking about new technology and billions of dollars at stake, there may not be enough.
Yeah, thank you so much. I really appreciate your discussion. Now I pass it back to Professor Vishnu.
Okay, thank you, Prof. Langsfong, and thank you, Prof. Jane. Actually, there is some still more than 5 questions, but I will inform to the audience. Prof. Jane is will give a lecture again, isn't it, Prof. Jane? Because we already around 2 or 3 times, so that maybe the people who the question is not have answer now maybe will will join again.
They can always send me an email.
Oh, okay.
They can always send me an email, because I don't want to wait 2 years to answer their question. No, the question may be out of date. I think they are free to send me an email, and I will do my best to respond, or I can ask my student to respond. It's not a problem.
Okay, thank you, Prof. Jane.
And you will make my presentation available to everybody.
Okay.
Right. I sent you the PDF version.
Okay,
so
thank you, Prof.
You can post it. I have no problem with that.
Okay, because we still have a opening ceremony in the.
Oh, okay, sorry. Yeah, so.
But maybe it is correct,
I don't want.
Pak Dr. Adila.
Yes, actually, yeah, tomorrow at 8:30.
Okay.
Yeah.
So no. So I think people need to have a good night's sleep and get up early to attend the opening ceremony.
Pak Setiadi or Pak Suryana, is there any comment, Pak Suryana? Prof. Jane, do you remember Pak Suryana, Dr. Suryana?
Yes, of course I remember Suryana.
Yes.
There is his photo. Yeah, there's Suryana. I should call him Dr. Suryana. Very nice to see you, Suryana. You look as young as 20 years ago. Great. Okay. Good to see you.
Okay. Thank you. Maybe because the time,
okay.
I will close with the statement. Okay. Ladies and gentlemen.
Please give my regards to Anyati.
Oh, okay.
Yeah.
Okay, I will send regard also to Prof. Anyati.
Yes.
Thank you. Thank you again from Prof. Jane for your very impressive and interesting discussion. Actually, we had a productive and inspiring time together with Professor Anil Jain, and this event about to come to the end. And me as a moderator, thank you very much to the all of you, the participant, very active participant in this plenary session. I hope you have found the very informative and helpful, and everyone can enjoy this event. Thanks again to Professor Anil Jain for your share knowledge. We hope to meet you again and in the other event. Okay, for the all of the participants, see you again, especially for the opening ceremony and the second day at the 8 o'clock. Maybe I don't know if Professor Jen, but maybe because the different time, because 8 o'clock in the 8 o'clock.
It's about 11 in the morning here, 10:48 a.m.
But in the US is a night, isn't it? When
No,
we
morning. Morning.
No.
We are behind. We are 11 hours behind.
when for example tomorrow in the morning.
We will have tomorrow morning.
Tomorrow morning at 8 o'clock.
Tomorrow morning.
Oh, you want me to be there?
No. I mean, it is night in your side, isn't it?
Yes.
Around 7.
9
p.m. 9 p.m.
7
in
in the
Michigan.
evening.
Oh, okay.
9 p.m. Michigan.
I mean, if you want me to be there, I can.
And I just also inform to you, we invite you again in the November. We will send. This is also
Okay.
another biggest event.
Okay. That's fine.
And opened by Indonesia President Pak
Okay.
Jokowi.
Alright.
So maybe the audience here
Okay.
maybe can join again to meet
Okay.
again with the
Sure.
Professor Jain.
Sure.
Okay.
Okay.
Thank
Alright.
you. Please
Thank
give
you very
applause
much.
again to Prof. Jain. Thank you very much. And
Thank you.
Can we have a group photo?
oh, photo. Okay, photo. Mbak Nia, you are special in the photo. Please guide us to make a good photo.
Oh, so you will take the photo,
Yes.
virtual photo.
Virtual photo. Mas Adila?
Yes. Mas Hamid or Mas Robi, could you please?
The committee is still in the our faculty, Prof. Jain. So
in campus, yeah.
in campus.
All right.
including me. So
All right. Okay. Great. Okay. Thank you.
thank you very much too. Yes.
Yeah. Bye-bye.
Hold
on. A photo with a photo.
Wait for the group photo.
Okay.
Could you count Mbak Nia if you will?
Saya kok nggak bisa jadiin gallery view gitu?
Oh, okay.
Kayaknya host deh yang bisa.
Okay.
Maybe I will count for the group photo.
Oh, you will.
Down and 1, 2, 3, and smile. Once more, please. 1, 2, 3, and smile. Okay, thank you.
So please send me a photo. Okay.
Thank you very much, Prof. Ani.
Thank you very much, Professor Jain.
Bye-bye.
Bye. Yes.
See you again.
All right. So I guess we are at the end of the first day, and don't forget tomorrow we will have, in addition to opening ceremony at 8:30, and after that we will have three plenary speeches from Professor Toshio Fukuda, IEEE President, Professor Akinori Nishihara from the IEEE Professor Kook Jin Chun, IEEE Vice President, and Professor Akinori Nishihara, the current IEEE Region 10 Director. And after that, in the late afternoon to evening, we have also keynote speeches at ICACSIS 2020 and IWBIS 2020. So with that, let me end with a good night to everyone. Have a nice night for at least maybe. So we are already very late, but hopefully we can see you guys tomorrow again. See you and bye-bye.
See you again tomorrow.
Yeah.
Thank you, everyone.
Prof. Lance, can you join us tomorrow morning in the opening ceremony? Hello, Prof. Lance. Are you still there?
Yes, I'm still here.
Yeah.
Okay. Yeah.
Will you join opening ceremony tomorrow morning?
Okay. All right. Yeah, normally, I supposed to go to church at that time, but anyway, I'll talk to the family. Okay.
At
Okay.
8:30 Indonesian time.
Yeah. So 8:30 in Indonesian time will be 9:30. Our time is
Oh
at
yes, in part.
okay, no problem.
Okay.
Okay then.
Okay. See you again tomorrow.
See you again,
Yes,
everyone.
you.
Thank you.
Bye. Good night.
Good
Night.
night.
I haven't dressed up, so therefore I didn't put out my video.
Oh, Prof. Lance, did you already send the PPT file to Mr. Adila
No,
and me?
no,
Not yet. Okay. Okay.
no, okay, no problem. Okay.
Okay.
Okay. See you tomorrow.
See you tomorrow. Okay, bye-bye.
Bye bye.